Hello everyone, I guess I am audible, and this is our third live session, Semiconductor Devices and Circuits. The course is being taught by Professor Sanjeev Sambadan, and today, as usual, we will be going to solve the problems related to the assignments that will help us to solve the assignment problems itself. And I guess we should start this session since it's already 3. We can start by 3 2. Okay, the attendance is quite low, I guess. So I guess it's advisable to start this session. So let's begin the session. Let's wait. Let's not wait for the others and admit the people if they joined. So let's begin our session. So our first problem states that we have to look into the body centered cubic lattice, and we have to calculate the number of lattice points per unit cell in a body centered cubic lattice. So this concept has already been taught in the lecture slides by the professor, and you can clearly see for the body centered cubic lattice what it has. If I draw, let me draw the cubic unit cell. If I will be able to draw it properly. Now what is happening with this? Okay, now I guess it's fine. So wait a second. Okay, so if this is our cube, so in the body centered cubic cell, what we will be having, we will be having the lattice sites or the atoms at the 8 corners like this. Okay, and there will be one along the body diagonal. If this is the face diagonal, let me draw it in another color. This is the face diagonal, and there is another diagonal which passes through the body. Okay, this is the, sorry, let me draw it in another color. If this is the face diagonal, then this is the body diagonal. Okay, and another atom, that atom will be located over here. It will be present just in the middle of this unit cell. So in total we will be having this one atom whole which contributes to the unit cell as a whole, and we will be having these 8 atoms which are lying at the 8 corners, and they are being shared between 8 unit cells. So we will be having 8 into 1 by 8 plus 1. So in total we will be having 2 lattice points. So we will be having just 2 lattice points per unit cell. In body centered cubic unit cell. Okay, let's be more precise. So among these, option D matches our answer, so we will select option D for this. Now moving to another problem which says that we have this zinc blende crystal structure. Okay, we have this zinc blende crystal structure. In the previous problem session, when we solved for the silicon crystal lattice, we saw that the unit cell had 8 atoms. It basically consists of 2 interpenetrating FCC lattices. Here this gallium arsenide, it has a zinc blende crystal structure. It's known by the name of the zinc blende crystal structure. In the case of the silicon, that was known by the name of the diamond crystal structure. Okay, so this gallium arsenide, it has a zinc blende structure. What does this zinc blende structure mean? It means that basically we will be having a face centered cubic lattice, and at each lattice point we will be having 2 atoms. So basically we will be having 2 atoms at each lattice point, of gallium and arsenide. Okay, one will be of gallium and another will be of arsenic. Okay, so gallium and arsenide will be present in this zinc blende kind of a structure. So first of all, we are having these two atoms per lattice point. Okay, and as we know, this face centered cubic cell, this basically has the cube basically has 6 faces, and on each face we will be having an atom which will be shared between the another cube. So in total this 6 faces will have 6 atoms which will be shared between rest of the another cube. Okay, so in total, in generality, we will be having 6 divided by 2 number of atoms at the faces, and at the corners we will be having 8 atoms which will be shared between the rest 8 cubes. So in total we are having 8 into 1 by 8 plus 6 into 1 by 2, which comes out to be equal to 1 plus 3 is simply 4. So this FCC has 4 lattice points per unit cell. Okay, so now we have to find the number of atoms per cubic centimeter. Okay, so we have to find the number of atoms per unit volume. That's what it's meant by the per cubic centimeter. So the total number of gallium arsenide atoms need to be found first. So the number of gallium arsenide atoms per unit cell are simply, we are having 2 atoms at each lattice point, and in total we are having 4 lattice points per unit cell. So we will be having 8 gallium arsenide atoms per unit cell. So this is the number of atoms. Now we have to find the volume of this unit cell, and we know since this is cubic unit cell and the lattice spacing is given by this value A equal to 5.65 angstroms, so we can find the volume. We can simply find the volume. Wait a second. So the volume because there is some issue with this. Okay, now it's fine. So the volume will simply be equal to A cube, since this is cubic unit cell. Okay, and A was 5.65 angstroms. So 1 angstrom is 10 to the power of minus 10 meters. Okay, so in total we are having the volume to be equal to 5.65 into 10 to the power of minus 10 raised power 3 meter, but we need to find it in cubic centimeter. So let me use 10 to the power of minus 8 centimeter. Okay, so let's use this to be in the centimeter only, since we require the answer to be in centimeters. So let's use the units to be centimeter only. So I will write here over centimeter cube. Okay, so let's calculate the value for this. It is simply 5.65 into 5.65 into 5.65. So it's approximately 180 it is coming out to be equal to 180.36. It's 1624. Okay, it's minus 24. So this is the volume. Now what we need to find, we need to find number of atoms per cubic centimeter. So number of atoms per cubic centimeter is simply number of atoms divided by volume. Number of atoms was 8 and volume is 180.36 into 10 to the power of minus 24. So it is centimeter raised power minus 3. Okay, the units of this number of atoms per cubic centimeter. So if we divide this thing, we will get it to be equal to 4.44 into 10 to the power of 22 per cubic centimeter. Okay, so this is the answer. Let's check the options. So the option B is matching our options and we will select this option B. Okay, now moving to another problem which says that we have this X-ray of wavelength 0.5 angstroms and it undergoes a second order reflection at an angle of 10 degrees from the crystal. So basically these X-rays they are getting reflected from the crystal and we have to find the spacing between the two atomic planes. And since you must have gone through the lecture slides, and in those lecture slides you must have seen this Bragg's law of electron diffraction. Okay, so in that we found that the distance between the two planes depends upon the angle of the incidence and it has to do with the wavelength whenever we want to have the constructive interference. So this 2d sine theta is equal to n times, where n is the integer multiple and this n is the order of the reflection, and in here n is equal to 2. So this is a second order reflection. Lambda is equal to, okay, it is equal to 0.5 angstrom and theta is equal to 10 degrees. Okay, so we need to find this d. D is simply n lambda by 2 sine theta. So it is 2 times, we have to find this in angstrom units. So let's keep lambda in angstrom itself, 0.5 divided by 2 times sine of 10 degrees. So it is simply 0.5 divided by sine of 10, or simply sine of 10. Let's calculate the value of sine of 10, and it is 0.1736 and it is 0.5 divided by 0.1736, so it's 2.88 angstrom. So the option D is the correct one and we will select this option. Now moving towards another problem which says that we have to consider a semiconductor, okay, and the semiconductor has a certain energy dispersion relation to the conduction band and it is given by E equal to A plus B times K minus C whole square, where these A, B and C are constants and we have to assume the mobility is mu 0. And from this we need to find the mean free time of electrons in the conduction band. So From this we know energy versus this energy dispersion relation is given by E equal to A plus B times K minus C whole square. Okay, this is the EK relationship. We know the effective mass is simply given by h bar square by d square E by dk square. Okay, why do we need this effective mass? We need this effective mass because we want to calculate the mobility. Mobility is given by q tau by m star. Okay, this tau is the mean free time of electrons. Okay, this is the mean free time between the collisions. Okay, so if we can find this m star, we can find this tau in terms of mu and the m star value itself, which will come out to be in terms of b, c or k, a constants. Okay, so what we will do, we will first derivate this dE by dk. Derivative of a is simply constant. It will come out to be equal 2 times b times k minus c, and its second derivative is simply 2 times b. Okay, from this m star comes out to be equal to h bar square by 2b, or mu times m star by q is tau. This is the scattering time. Okay, so mu 0, so it's h bar square times h bar square by, okay, 2b times q is our tau. So this is the value of the mean free time. Okay, so if we check the options, mu 0 h bar square by 2bq, so option C is the correct option to go with. Okay, now moving towards another problem which says that uh, the electron in an n-doped silicon crystal suffers scattering, and the scattering is only due to the lattice vibrations. Okay, and the interaction of the impurity and its interaction with the impurity. So basically we will be having this, we are having just the phonon scattering, okay, which is the dominant one over here, and another we are having is impurity scattering. Okay, we are having these two scatterings. So it has been told to find what happens at extremely low temperature. What does the mobility depict to us? What does it show to us when we have very low temperature? How does it behave with the temperature? How does it behave with temperature? With increase in the temperature. However, the temperature at that time is extremely low. So basically what we have written over here is that at very low temperature region, the lattice vibrations will be suppressed. Okay, there will be less scattering at low temperatures. There will be less scattering. Okay, so this phonon scattering theory will go, and the scattering will be only scattering will be due to impurity ions. Okay, so this is at low temperature. So this is at low temperature. So now if we increase the temperature at low temperature I am talking about, then the electrons will spend less time around that impurity scattering event, okay, because that impurity scatterer, it will have less interaction with the electron itself now, because the electron has some energy, and as a result of this, some more, for example, if T is equal to 10 Kelvin and T is equal to 20 Kelvin, at T equal to 20 Kelvin, the electron will be having the little more energy than T equal to 10 Kelvin, and as a result of this thing, it will spend less time around this impurity, and thus the impurity scattering will be less, and as a result of this thing, the mobility will increase, okay, the mobility will increase with the increase in temperature at low temperature only, okay. So if I draw this mobility versus temperature curve, it will simply look like, so if I draw the mobility versus temperature in the log scale kind of a thing, so it will look like this, okay, temperature, mobility, and you can say this region at low temperature is dominated by impurity scattering, and this region is dominated by lattice or phonon scatter, okay. So this is the consequences of the temperature on the mobility. What does it do with the mobility? Now it says that this second question, this another question, it says that we have to consider a 1D LEDs with LEDs constant to be equal to A and crystal length to be equal to L. So it says that where do we observe the energy band gaps? So energy band gaps, as you have seen that one for 1D crystal, if this is the spacing, we will be having these atomic potentials that will be interacting with each other, and as a result of this thing, we will be having the interacting potentials, and we will be having a band gap, or I shouldn't say band gap, it's not always the band gap, it's actually the band gap, but I would say the gap, it is the gap originates at the integer multiples of pi by a, okay. So it occurs at the integer multiples of pi by a, as you must have seen how that parabolic relation of the ek which we obtained from the Croning-Penny model in the lectures. When we obtained it, we saw that it was not a continuous parabola, but it was somewhat like this kind of a thing, okay, somewhat like this, okay. Then we had a gap over here, we had something like this, okay. It was not a continuous, we had some gaps over here, those occurred at the pi by a, okay, at the at those edges, okay, pi by a minus pi by a, okay. Similarly this would have been 2 pi minus 2 pi by a, okay. That's what we saw in the that Croning-Penny model, okay. Energy band diagram, energy, sorry, not energy band diagram, energy band structure kind of a thing, because this is ek relations. So from this, what we can deduce is, we can say that the option A among these is the correct option. So the gaps arose at the energy that integer multiples of these pi by a. So that was the one of the conclusions from the Croning-Penny model when we drove it, okay. It was like this, what we obtained, some that there was this edges were not perfectly parabolic, and the gaps arose, and it depended on the lattice spacing. This 2 pi by a, which was a given by the a in case of the 1D lattice. So now there's another problem. This is just this simple statement which says that what is a Brillouin zone, and we know that the Brillouin zone is it is just the reciprocal space. Okay, it is just the K space. Okay, that contains the solution to the wave functions. You have seen that how Fourier transform, we used it to transform from one from time to frequency, and similarly in here we transform from the real space to the reciprocal space. So the option A is the correct option. Okay, wait a second. Okay, so this option A is the correct option to go with. Now another problem which says that uh, we have to consider the 1D band structure which is given by h bar vf vf of kx is E. Okay, so we have to find the effective mass for this. So we know that this will be having first derivative which will be constant, and second derivative will not exist at k equal to 0, because this is we can say this is a modulus function. So as a result of this thing, this d square e by dk square does not exist at kx equal to 0. So for this thing, hence the effective mass is not defined. Okay, so we will select the option B, because second derivative does not exist, hence the effective masses does not exist for this kind of a thing. Now moving towards another problem which says that we have to see the Bloch's theorem for a periodic potential, and it is given by psi of x plus a is psi of x exponential of e to the power iota ka. Okay, where the a is this Light's constant, and u of x is the periodic potential, that is u of x plus a is same as u of x. Okay, it has the periodicity of a, which is same as the Light's constant. So from this, what we are going to find, we are going to look into the this thing which is the alternative representation of this Bloch's theorem. Okay, we have to find the alternative representation of this Bloch's theorem. So simply we can say that psi of x plus a is simply it is simply u of x plus a e to the power of ikx plus e to the power of ik of x plus a. Okay, but this u of x plus a is simply u of x, and this e to the power iota kx, and this is simply e to the power of iota ka. So this psi of x, this is simply equal to psi of x, okay, e to the power of iota k Okay, so we have found out this to be equal to, simply equal to u of x e to the power of iota k a. Okay, so the uh, u of x. Okay, so this is simply equal to u of x times e to the power of iota kx. Okay, so now moving towards the another problem, which says that we have to find out the molybdenum. For the molybdenum, we have to find out the the atomic, we can say this, percentage of this cubic unit cell that is occupied by the molybdenum atoms itself. Okay, so if we see this molybdenum, it is basically a body centered cubic structure. It has been given to us, it is body centered cubic structure. So there will be, what you can say, there will be in general two atoms of this molybdenum present in this cubic unit cell. However, let's draw this cube first, because we need to find the this radius of the molybdenum atom, which is given to be equal to half of the center to center spacing of the nearest neighbors. Okay, it is given by the half of the center to center spacing of the nearest neighbors. So if we draw this cube, and this molybdenum will be present over here, let's say, and it will be in the body, and it will be along the another face as well. Okay, so actually I'm not able to draw it properly, but it will be like this. Okay, this will be touching this thing. Okay, so basically let us erase this thing and let's draw it to be perfect. Okay, so it will be touching this thing. This is not a perfect sphere which I have drawn, but let's assume it to be a perfect. And what it says that, it says that this since this is this body diagonal. Okay, this is this body diagonal, this is the face diagonal, and this is the lattice spacing a, this is the lattice spacing a. Therefore face diagonal length, if I calculate face diagonal length, is simply equal to a square plus a square under root, it is root 2a. And for this cube diagonal, which is going through this middle, this cube, which is this cube diagonal, this cube diagonal length is simply given by, this is now this value, now this whole value is root 2a. Okay, this whole value is root 2a, so it will be 2a square plus this side is having the value of a, so it is a square, and we will be having this to be equal to root 3a. Now the center to center spacing, this center to center nearest neighbor spacing is half of this, is half of this. So basically we will be having this to be equal to root through 3a by 2. So the radius is now half of the center to center nearest neighbor spacing, and therefore the radius of this MO atom is simply root 3 by 2a by 1 by 2. or simply it is root 3a by 4. Okay, this is the radius of the MO atom. So the volume of MO atom is simply considering it to be a spherical 4 by 3 pi r cube, or simply it is 4 by 3 pi times root 3 by 4 a cube, and it is simply this 4 and 4 will go, it will be 3 root 3, it will be pi times root 3 a cube by 16. So the now the total volume occupied by MO inside this body centered cubic cell is simply number of atoms of MO times the volume of atoms. Okay, this volume. So number of atoms in body centered is 2, and this volume came out to be equal to pi root 3 a cube by 16. So it is simply pi root 3 a cube by 8. Now the total volume will simply be given for this cube. The volume is given to be equal to volume of cube is a cube. So the percentage of volume percentage, let us write down like this, volume percentage of cube occupied by MO atom is simply that value we obtained, this thing pi root 3 a cube by 8, pi root 3 a cube by 8 divided by a cube into 100. So let's solve for this. If we solve for this, it is pi times root 3 divided by 8. So it comes out to be equal to 68%. Okay. So it comes out to be equal to 68%. It is 68%. Okay. Now moving towards another problem, which says that which of the bands will have heavier electron mass. So I would like you to answer this question by just typing in the chat if you want, or if you want to unmute, even you can unmute yourself and answer this question, because this is just the logical question that we are going to face again and again if we are going to deal with the effective masses. And this effective mass kind of a thing, it gives us an rough estimate of the theoretical mobility. Higher the effective mass, lower will be the mobility, because if mobility had the dependence, which we saw, mobility was inversely proportional on the effective mass. So, okay, m of a is less than, okay, so as rightly pointed out, sorry, I don't know what happens sometimes with this pencil, as rightly pointed out, m star, because this thing has more curvature. So what does this show? This curve A, basically this curve, we have to look into these curves and deduce Don't know what is happening with this thing. Sorry. So basically we have to look into the curvatures of these curves, and from this we can clearly deduce that the curvature of A is more than the curvature of B, and as a result of this thing we will be having, since this curvature thing, this effective mass is given by h bar square by d square E by dk square. Thus for sorry thus for uh, m star of A will be less than m star of B. Okay, and as rightly pointed out, there will be heavier electron mass in the we can say in the energy band B. Okay, energy band B will have the heavier effective mass as compared to the energy band in the A. As you must be aware of these things when you do this transitioning from one band to another, that if there are two valleys in this, for example in some material we are having two valleys, and sometimes an electron moves from one valley to another valley, its properties changes drastically as compared to the first, because it has changed its what you can say in the surroundings. Now it is in different valley, it has now different energy, and it has now different curvature, and because of that curvature we will be having different effective mass, and as a result of this thing we will be having different velocity, different mobility. Okay, so now moving to another problem. This kind of a problem was not there in the assignment, about this reciprocal lattice, but I thought that it would be good if we just do one problem about this reciprocal lattice. So this problem basically says that we have to show that for a reciprocal lattice of hexagonal Bravais lattice, the reciprocal lattice is also hexagonal. Okay, if we are having a hexagonal Bravais lattice, what does it mean? It means that we are having two sides to be equal, and the angle between those two sides is 120 degree, and the third side is not equal to those particular two sides. For example, if we have three lattice vectors, say A, B, and C, and the magnitude of A is equal to magnitude of B, and the angle between vectors A and B is 120 degree, then the angle between A and C will be 90 degree, and also the angle between B and C will be 90 degree. Okay, so that's what it is meant by hexagonal lattice. So this if A, now if I say that A is the lattice vector along X, okay, so along B, these are the directions what we are mentioning. Along B we are having it to be equal to A by 2 plus root 3 by 2, sorry, root 3 by 2 A y hat, and along C we are having it to be equal to C1 times Z hat. Okay, as you can see, the magnitude of A is equal to magnitude of B, and the angle between them is 120 degree. Now the professor taught us the reciprocal lattice vector, and the reciprocal lattice vector in the direction of A will simply be given to be equal to 2 pi by volume. Volume is A dot B cross C, simply. This is multiplied by the B cross C. So this is how we find out the reciprocal lattice vector for different, we can say different directions. Okay, so if we now find this B cross C first, B cross C, we can say it is simply x hat, y hat, z hat, this is a by 2 root 3 by 2a, this is 0, this is 0, this is 0, this is c1, and this whole thing is simply, it will simply be uh, x hat root 3 by 2 ac1, and when I do this, this will be minus times y hat a by 2 c. Okay, yes, it's correct. And now for the volume is simply a dot b cross c. B cross c we found out, and now a dot, this thing is simply a x hat dot root 3 by 2 ac1 x hat minus a by 2 c1 y hat. So the dot product will simply be with this x dot x will be 1, and with this x dot y it will be 0. So we will be left with simply root 3 by 2 a square c1. So this is the value of the volume. Now if we put this value back over here, okay, let us put this value back over here. It will simply be a is equal to 2 pi, b cross c is simply, b cross c is x hat root 3 a by 2 x hat root 3 a by 2. Okay, c1 is also there, c1 minus times a times c1 by 2 y hat divided by the volume, which is root 3 by 2 a square c1, root 3 by 2 a square c1. Okay, so it is simply, if I take this to be common, this will simply be equal to 2 pi by a square c1 times a c1 times root 3 by 2 x hat minus 1 by 2 y hat divided by root 3 by 2. This c1 and c1 will go, this a will go with this thing, and we will be left with 2 pi by a x hat minus 1 by root 3 y hat. So this is the reciprocal lattice vector A. Okay. Now the reciprocal lattice vector B is simply 2 pi by a dot b cross c times c cross a. Okay, c cross a needs to be found out. C cross a is simply x hat y hat z hat, and the c is simply 0 0 c1, x is simply a 0 0, and this will simply be equal to, if I say for x it is 0, for y it is minus times a minus of ac1, so it will come out to be equal to ac1 y hat, and for z it is 0. Okay, so this is the value of c cross a. So this vector b is simply 2 pi by volume is root 3 a square c1 by 2 root 3 by 2 a square c1 and this came out to be equal to a times c1 y hat, a times c1 y hat. So this c1 will go with this, a will go with this. So we will be left with 2 pi by a, 2 pi by a, 2 by root 3 y hat. Okay, so this is the reciprocal lattice vector b. Now what about reciprocal lattice vector c? So this reciprocal lattice vector c is simply given by 2 pi times a cross b divided by the volume, which is a dot b cross c, which is simply, we need to find this a cross b, simply x hat, y hat, z hat. So this will be a 0 0, this will be a by 2, this will be root 3 by 2a 0. Okay, so it will simply be x hat root 3 by 2 a square z hat. Okay, because when I do this, this 0 into 0, this is 0. When I do this, this will be 0 and 0. Only when I do this, I will be having this component along this z, and it will be given by this thing. Sorry, it isn't x hat, it is z hat. Okay, so this is the a cross b value, a cross b value along, it comes out to be along z. So the c vector is simply 2 pi a dot b cross c was simply root 3 by 2 a square c1. This is root 3 by 2 a square z hat. So this c, sorry, this c is there only, it won't go. Sorry. So this c1 is there only, it won't go. However, this a square will go with this, this root 3 by 2 will go this. So we will be left with 2 pi by c1 z hat. So this is the reciprocal lattice vector c. Now what we need to find out is the magnitude and the angle between these reciprocal lattice vectors. So the first of all, let's find out the magnitude of reciprocal lattice vector a. Okay, magnitude of reciprocal lattice vector a. So a was, wait a second, so a is this thing 2 pi by a times x hat minus 1 by root 3 1 by root 3 y hat. So the magnitude of y is a, this a reciprocal lattice vector is simply 1 square plus 1 by root 3 whole square. So it is simply 4 by root 3 and 4 by root, okay, it is 4 by 3, then it is 4 by root 3. So it will be simply 2 pi by a times 2 by root 3. So it's the magnitude of this reciprocal lattice vector a. Now the magnitude of reciprocal lattice vector b is simply, okay, it is simply 2 pi by a 2 by root 3. Okay, it is simply 2 pi by a 2 by root 3. So this is also done. This is the magnitude of reciprocal lattice vector b. Now we can use these magnitude values and we can say the dot product between a and b is simply the a multiplication of the magnitudes of a and b times the angle between them, cos of the angle between them. So this is a dot b is simply a into b cos of theta. So a dot b is simply, it is 2 pi by a, I guess it was simply x hat, and it was some minus term over here, minus 1 by root 3 x minus 1 by root 3 y hat. Okay, dot product with 2 pi by a, dot product with 2 pi by a, 2 by root 3 y hat, 2 by root 3 y hat. Okay, so if we do the dot product, it would simply be 2 pi by a whole square minus 2 by 3. Yes, this is the value of this dot product. Now if I substitute this value in, let's name it equation 1, let's name it equation 2. So if I substitute 2 in 1, sorry, so if we substitute 2 in 1, it will be simply 2 pi by a square, 2 pi by a whole square minus 2 by 3, I guess it was, let me check, minus 2 by 3 is simply equal to 2 pi by a, 2 by root 3 into this is also 2 pi by a, 2 by root 3 cos of theta. Okay, this 2 by a and 2 by a will go with this thing, this root 3 into root 3 is 3, and this will go with this 2 will go with this, and we will be left with minus 1 by 2 is cos theta. Okay, or theta is cos inverse of minus 1 by 2, and you can clearly see that this is cos inverse of minus 1 by 2. Okay, so this cos inverse of minus 1 by 2 is simply 120 degrees. So the angle between reciprocal lattice vector A and B is 120 degrees. So we can write it like this: angle between A and B is 120 degrees. Okay, now what about the A dot C? A dot C is simply 2 pi by A times x hat, sorry, x hat minus times 1 by root 3 y hat, minus times 1 by root 3 y hat, dot C is simply 2 pi by C1 z hat, though, so it is simply equal to 0. Okay, and similarly for this uh, B dot C, so it clearly says that the angle between A and C is 90 degree. Okay, so you can say that angle between reciprocal lattice vector A and C is 90 degrees. Similarly for B dot C, B came out to be equal to 2 pi by A, 2 by root 3 y hat, dot 2 pi by C1 z hat. So it is simply also equal to 0. Thus the angle between B and C reciprocal lattice vectors is 90 degree. And also the magnitude from the previously derived values came out to be the magnitude of A was equal to magnitude of B. However, it was not equal to magnitude of C, because magnitude of C is simply 2 pi by C1. Okay, it is not equal to the magnitude of C1. C and angles between A and B is 120 degree. So what you can say is, therefore a reciprocal lattice is also hexagonal. Okay, so we have been able to find out that the reciprocal lattice vector of a hexagonal Bravais lattice will also be hexagonal. Okay, so this was the important conclusion from the result, that if we look into the reciprocal lattice vector of a hexagonal Bravais lattice, then it will also be the hexagonal itself. Okay, now let us move to another problem, and please, if you can type about the problem solution, because it's just a theoretical problem. It says that we have an energy band diagram, and we have to find the electric field, and how is this electric field related to the conduction band. Okay, so if you feel that you can answer this, you can type in the chat, or you can even unmute yourself if you want to answer. Let it be wrong, there's no problem. So let me give you a hint. The hint is like this: the electric field is the what you can say is the derivative of the uh, potential. Okay, spatial derivative of the potential. By spatial, I mean, for example, that is d by dx of some potential is the electric field. I'm just giving some hints about this problem. Okay, so nice. So it has to do with the this conduction band edge. This EC basically is the conduction band edge. Nice try. I appreciate it. It's really nice that you tried. So we can say that this electric field is simply minus dV by dx. This you have already done in the I can say in the 11th or 10th classes of yours. And what does this energy band diagram represent? Energy band diagram basically represents the energy levels of electrons. Okay, so let me write it like this energy band diagram represents energy levels of the electrons. So for an electron, if we relate this energy with the potential, it is simply minus q times v. Okay, this is the relation between the we can say the energy and the potential. So if we take this EC as a reference now, because EC or EV, they are both energy levels. Okay, EC as a reference. Okay, then this electric field is simply equal to this, from this you can see V is equal to minus E by Q. Okay, simply. So if I put this value of V, in equation 1, so it will be simply minus of minus will simply by dEc by dx times 1 by Q. So I guess you must have gone through this derivation what I have done. It says that the electric field is given to be the is given by the derivative of the conduction band, okay, energy level. So for example, if I have, let's say, the energy band diagram like this, if this is my EC and this is my EV, uh, okay, absolutely correct, absolutely correct. Option C is correct. You are correct in this. So if this is my energy band diagram, okay, so uh, this signifies, since there is a slope in EC, okay, it is linear slope, okay, linear. Since this is a linear slope, it means that the electric field is constant, okay. It means that the electric field is constant because uh, the slope of this line is linear, okay. That's what I have written over here. Similarly, the direction of the electric field is like this. Electric field points upwards, okay. So the direction of the electric field is in this what energy band diagram I have drawn over here, it is like this, okay. So this is about this energy band diagram, that the derivative of this conduction band edge, the spatial derivative of this conduction band edge, it can help us to find the electric field, and the electric field is simply given by derivative of this conduction band edge or the valence band edge. It is simply the derivative of the energy, spatial derivative. Now Now we have another problem which says that we have n-type semiconductor at 0 Kelvin, okay, and we have to locate the Fermi level, okay. Let's be clear. Oh, sorry. At T equal to 0 Kelvin, okay. So we are basically at 0 Kelvin, and we have to locate this Fermi energy level, okay. So we have to locate this Fermi energy level. Can you just let me just give some hints first, then you can try to answer this question. So at T equal to 0 Kelvin, so what does this Fermi Dirac statistics tell about? They tell us that this Fermi Dirac, let me write it down over here, this Fermi Dirac statistics tells that all the states below the Fermi level should be filled with electrons. Okay, this is point number 1, and point number 2 is that they at this temperature, which is low temperature, okay, we know that this Fermi level will can be, it can be even inside the conduction band, and it can be even inside the valence band for the degenerately doped semiconductors, okay, and it can be even in the middle of the band gap, which will be simply between the conduction band edge and the valence band edge, and also it can be between this, what it is written over here, that donor level and the conduction band edge. So since it has been given, one hint is given about the donor level, so we need to check about the properties of the donor level as well. So at 0 Kelvin, what happens? At 0 Kelvin, there is no energy for these dopant atoms to be ionized, okay, they cannot get ionized at this 0 Kelvin, because the thermal energy is very less, it is 0, okay, they cannot go from this donor level to the conduction band edge. So this donor level has to be filled, these donor level states, they have to be filled at this 0 Kelvin, okay. So uh, so they, we can write it like this, that no dopant atoms could be ionized due to absence, or can say lack of energy, due to lack of energy, and the donor states will be filled with electrons. Okay, so from this, can we now comment about the Fermi level, where it should be? We have seen that the donor level has to be filled, and we can say this semiconductor, uh, okay, D, absolutely correct. So the option D is between this donor level, and the conduction band edge. This is where it should lie, because all the states below this Fermi level should be filled with electrons, and that's what we need. We want this donor level to be occupied, because we are having no thermal energy for these dopant atoms to be ionized. So the Fermi level, as rightly pointed out, will be between the this donor level and the conduction band edge. Absolutely correct. So now let's move to another problem. Now this is a numerical problem. It says that we have an intrinsic silicon wafer was there, and it was doped with the phosphorus atoms, and the doping concentration is about 5 into 10 to the power of 16. So basically, what is this phosphorus atom? Phosphorus atom is, it is a pentavalent, so it has 5 electrons. So as a result of this thing, phosphorus atom, it will act as donor impurity, okay. So this phosphorus atom will act as a donor impurity, and it will have the concentration of 5 into 10 to the power of 16 per centimeter cube. So this is the concentration of these donor atoms, because this phosphorus, they have 5 valence electrons, and as a result of this thing, when they bond with this silicon, they donate the 5th electron, and we will be having an this electron and the extra electron and the ionized donor impurity. Overall, the silicon will remain charged neutral, because we have this positively charged donor and the electron which has been generated because of this new bond formation, and we can say that now this free electron, this will enhance the carrier transport, and this will act as the n-type doping, okay. So this Nd is due to this phosphorus, and this boron, this boron has 3 valence electrons, and as a result of this thing, it creates a hole and results in the p-type doping, okay. So this Na is the due to boron, and it is 6 into 10 to the power of 16 per cubic uh, centimeter. Okay, per cubic centimeter. So now we have to assume that at 300 Kelvin the intrinsic carrier concentration of silicon is 10 to the power of 10, and we have to assume that all the dopant atoms are ionized. So we have to say that that all the dopant atoms that we had, they have given a free electron, or they have been able to produce the free hole. Okay, so from this we have to find the location of the Fermi level with respect to the conduction band edge, at the 300 Kelvin, and we have to assume the effective density of states at the conduction band edge to be given by this value Nc. So basically, actually, the density of states at the conduction band edge, they shouldn't be like this. The carrier concentration at that point should be 0. But since we are dealing with the mathematical problem, we assume all the states to be located at the conduction band edge, because we know the Fermi statistics very well, that they decay with the energy, and the product which professor taught us in the class, that how the G of E into F of E will give us the electron concentration, and how it is localized, or it is, can say, located near the conduction band edge itself, because the long the not long, because the energy carriers having high energy will not be able to uh, participate in the transport mechanism because of the Fermi Dirac's decaying tail. Okay, so that has to be taken into account, that this is the effective density of states which is located at the conduction band edge. Now overall, since this Na is greater, I guess it's greater than Nd. Clearly it is greater, so it is greater than Nd, so therefore we will be having some effective doping. We have doped the semiconductor, the silicon semiconductor, at the same time with the N type as well as at the P type. But the P type doping is more, I guess. It's more. It's 6 into 10 to the power 16. So the effective doping P type is equal to Na minus Nd. Sorry, Na minus Nd. So it is 6 into 10 to the power of 16 minus 5 into 10 to the power of 16. It is 10 to the power of 16 per centimeter cube. Okay. And now this Na minus Nd, this is also much greater than Ni, clearly, because Ni is having the value of 10 to the power of 10 only, and Na minus Nd is 10 to the power of 16. So we can say this whole thing, since it is P doped, now it will be having the whole concentration to be equal to this Na minus Nd. Okay, so this Na minus Nd is simply now the 10 to the power of 16 per centimeter cube, and the electron concentration, will simply be given by the law of mass action, that is N into P is equal to Ni square, and Ni is 10 to the power of 10 whole square, P was 10 to the power of 16, so it comes out to be equal to 10 to the power of 20 divided by 10 to the power of 16, and it is 10 to the power of 4 per centimeter cube. So this is the concentration of the electrons. Now we know that the concentration of electrons is simply Nc times exponential of minus times Ec minus Ef by kT, or simply Nc times exponential of Ef minus Ec by kT. Okay, if we take ln on both sides, it will simply be ln of n by nc times kt is equal to ef minus ec. We have done all this because we wanted to locate the Fermi level with respect to the conduction band edge. So you can say that this kT is the thermal voltage at 300 Kelvin. It is equal to 26 milli electron volts approximately. Actually, it is 25.9 milli electron volts, but we take it to be, for the calculation, we take it to be 26 milli electron volts. It is 0.026. Ln of n is 10 to the power of 4. Nc is, let us see, it is 2.8 into 10 to the power of 19. It is 2.82 into 10 to the power of 19. So this is the value of this EF minus EC. So now if we calculate this value, it is 10 to the power of minus 15. Minus will come outside. So it is simply minus 15, 0.026. It is 35.36 into 0.026. So it is coming out to be equal to EF minus EC is minus 0.92 electron volts, or simply EC minus EF is 0.92 electron volts. Okay, so we have been able to find the location of the Fermi level with respect to the conduction band edge. Now moving towards another problem, it says that we have an intrinsic germanium. Okay, so this intrinsic germanium wafer, it is doped with shallow acceptor impurities. Okay, since it is doped with shallow acceptor impurities with a density of 3 Ni by 2, and Ni is the intrinsic carrier concentration. Okay, intrinsic carrier concentration at temperature T, all acceptors are ionized. Okay, so it means all the acceptors are ionized, and we are having no donor impurities. Let's be clear about those. Okay, so let us write down the solution for this. It is Na, all are ionized, all acceptor impurities are ionized. So Na minus is Na, it is simply 3 Ni by 2, which is this value. Okay, this value. And since this all the these acceptors are ionized at this temperature, and we will use this charge neutrality, N plus Na minus is simply P plus Nd plus. This is by using charge neutrality. Okay, so Nd plus is equal to 0. There are no donor impurities. We have been not given any information about that, so we will take those to be equal to 0. And now it simply means N plus Na minus is simply 3 Ni by 2 is simply equal to P. Now if we use this law of mass action, we can say simply this N into P is Ni square, or N is simply Ni square by P. Okay, so this N is simply Ni square by P. So let's replace this N with this Ni square by P plus 3 by 2 Ni is equal to P, or simply it will be P square minus 3 by 2 Nip minus Ni square is equal to 0. Okay. Now let's solve this quadratic in P. So it will simply be, the concentration cannot be negative, so we will take only the positive. So it will be 3 by 2 plus times 9 by 4 Ni square plus 4 Ni square by 2. So it will be simply, so it's Ni also here. Okay, 3 by 2 Ni. So it is 4 into 4 and 16 plus 5 plus 9 is 25. 25 is 5. It is 5 Ni by 2 divided by 2, or simply it is 5 plus 2. It is simply 5 plus 8 divided by 4, which is 2 Ni. So this is the whole concentration. Okay, the whole concentration came out to be equal to 2 times Ni. Okay, fine. Okay, now let's move towards another problem, and I guess this will be today's last problem. So it says that under which condition the position of Fermi level in an intrinsic bulk semiconductor lies exactly at the middle of the band gap at a non-zero temperature. Okay, at a non-zero temperature. So it is some temperature which is given to us. So if we now try to solve for this, what we have to do is we have to say that this intrinsic carrier concentration is simply given by Nc times Nv exponential of minus Eg by 2 kT, where Eg is the band gap. Eg is the band gap. Okay, Eg is the band gap. So this is the intrinsic carrier concentration, what we found out in the lectures which professor taught us. So if I take the ln of this expression, it will be simply ln of Ni is simply ln of Nc Nv under root minus Eg by 2 kT. Let's name this as equation 1. And also we know that for an intrinsic semiconductor, this Ni in terms of the intrinsic Fermi level is simply given by Nc exponential of, let me write this as exponential because it sometimes creates confusion whether it's E or exponential of minus Ec minus EFi by kT. Okay, so it is, this is in terms of the intrinsic Fermi level. Okay, so this, if we take the ln for this expression, it will simply be, if I take the ln for this expression, it will simply be minus Ec will go with this thing, so it will be simply ln of Ni minus ln of Nc. This whole thing will be multiplied by kT plus Ec is EFi. Okay, so this is the expression for this EFi, intrinsic Fermi level. So now if I use equation 1, which is if I replace this ln of Ni with this equation 1, so let me write it down. Replace ln of Ni using equation 1. So it is now simply kt times ln of root of NCNV minus Eg by 2 kt, okay, minus Eg by 2 kt minus ln of NC minus ln of NC, okay, minus ln of NC plus EC, okay, is EFI. So this will be simply kt ln of, this is root of now NV by so it will be simply root of minus is this thing, so it will come out to be in the denominator. So if I put a minus sign over here, so it will be kt ln of NC by NV minus Eg by 2 kt plus EC is EFI, or simply this is simply EC minus Eg by 2 minus kt by 2 ln of NC by NV. Sorry, it should be NV over here. What is happening with this thing? Why isn't it selecting this eraser? Okay, so it is NV, okay, is EFI. So this is the intrinsic Fermi level. Now this NC is the effective density of states, which professor taught us, and for 3D material it came out to be equal to 2 times 2 pi mn star kt by h square 3 by 2, and NV was 2 times 2 pi mp star, this is n, this is not h, okay, kt by h square 3 by 2. So from this, if I divide NV and NC, what we will be left with, NC by NV is simply mn star by mp star raised power 3 by 2, okay. So if I use this NC by NV value and I put it in equation 3, put NC by NV value in equation 3, what we will get is, we will get EFI is EC minus Eg by 2 minus 3 by 4 kt ln of mn star by mp star, okay. This is what we get. This is what we were after. We wanted this expression, which is this ln of mn star, it to be in the terms of the mn star and mp star. Now if mn star is equal to mp star, okay, then we have this expression to be equal to, this has this thing will be equal to ln of 1, and ln of 1 is 0, and EFI is EC minus EG by 2. So simply, simply it means that what we have found out is that the intrinsic Fermi level will lie in the middle of band gap if this condition holds true, if effective mass of electrons is equal to effective mass of holes. Okay, so this will hold true only when the effective masses, both the effective masses are same. Then we will be having the intrinsic Fermi level lying exactly in the middle of the band gap. So I guess that's it from my side for today. So if you have any questions regarding today's problems or anything you want to ask, you can unmute yourself or you can type in the chat also. So uh, otherwise, if you have no queries, we can end the session and you can join another session which will be after this session, just after this session, and that will start around 5. So you are free to leave the session if you have no queries.
Hello.
Hello.
Am I audible?
Yes, you're audible.
Actually, this tutorial session I have joined today only.
Okay.
So the previous sections, can I download the videos from that link given? This is third class, right?
Yes. It's that class only, and you can find all the links in the Excel sheet. They have provided it in the course itself, and
Okay.
you can access every video. It's on they are on the YouTube itself.
Okay. And next session is based on this related to this itself, or any
Uh,
idea?
I guess it will be related to this only, most probably. So it will be related to, and I guess there will be some more problems that will be solved in that, some new problems itself.
Okay.
So if you have some spare time, you can join that, or if you have, if you want to skip the, for example, any lecture, they are always available at your disposal. You can uh, join anytime the YouTube video which will be present for you. We will be uploading the YouTube video link right after the class ends. So if any of you misses the class, he is he has the freedom or liberty to join the class even after the class has ended. Only one thing is there, that he cannot ask the questions, but he or she can type or write us an email if you have any query regarding any problem, for example. You are always welcome to ask us through an email, and we will be happy to respond to you all. Okay.
Okay, so regarding the assignments, will I solve assign some assignment questions? Some doubts will arise. So can you clarify that? Uh, or
Yes, absolutely. We can absolutely clarify those as well. So for that, what I want you to do is that, for example, if you have certain problems that you want us to discuss only after the assignment is submitted, you can drop an email and say that we want to solve, for example, problem number 3 from the assignment number 1, problem number 4 from the assignment number 1, and we will solve that problem in the assignment, sorry, in the live session itself. Okay.
okay, so also it is like after submitting the assignment, we can ask the questions related to that, right?
Yes, you can even ask before, for example, if you have confusion and you are solving some assignment. Okay.
Mm.
and you want some hints about that solution, for example, you can drop an email. We can respond by an email. You do not have to
Or
wait. You
okay.
Okay.
And one more thing, suppose if I am solving, can I share the screenshot what I have done so that if you can check whether where is the issue like that.
So yes, yes, you can share the screen, and I would rather say that the much easier thing will be if you solve if you're solving any question, you just and you have doubt whether you have solved it correctly or not, you can just drop an email. We can check the solution and we will tell you, for example, there is a mistake over here. You do not have to wait a whole week just to get one point clarified. We can
Okay.
help anytime. Okay,
Okay,
regarding email as well.
because the two assignments are over, and when the result came, some questions I have some doubts. So if I post that question with what I have solved, you can clarify in the next class, right? All
Yes,
this
yes.
one.
Okay,
Okay,
okay. It's
okay,
fine. You can just
okay.
drop me an email.
Mm.
Uh, okay. You can just drop me an email. My email address is this. You can see.
Okay, mail address
Okay.
80 that one
Yeah. Yes.
80
This.
EAB 20.
Yes. You can drop me an email. Okay.
Okay, thank you.
Okay. Fine.
And the session is good. Thank you for the time.
Okay. Okay. Fine. Thank you.
Okay.
So I guess if you have no question, we can end this session.
Okay,
So
thank you.
okay. Fine.